So we have example 11 on page 347, yeah, our grade 10 siyavula ne. So I'm just referencing the book so that we know where we take it from. We are doing a problem here, waters of crystallization. So we're given that aluminium chloride, AlCl3, is an ionic substance. So ionic means that when it's added to water and then dissolved, then really an ion, a positive, yeah, aluminium, and we have an aluminum ion and we have chlorine ions. So because chlorine has valence electrons where it receives one, then that means there's three of these. So you'll have one aluminum and then three chlorine atoms around it. So in ionic solution, we'll know that you'll have the aluminum forming ions on the side and then the chlorines forming other ions as well. So the water molecules may be trapped inside the crystal lattice. So the aluminum trichloride is an ionic substance and it forms crystals in the solid phase. So when it's a solid, it forms crystals. I guess salts also are another example of crystalline structures. And then there are other things as well. But for now, like geological formations, a lot of rocks are crystalline formations. But yeah, it's a conversation for another day. So when we have this, water molecules, so H2O, may be trapped inside the crystal. So you're seeing now we're getting closer to why it's called waters of crystallization. And when there's water trapped in the crystal, we write then the formula as AlCl3 times NH2O. Now we're told that a learner has heated some of these crystals until all the water had evaporated. So when all of this water has evaporated, otoshalaga the aluminium trichloride, and after that heating, so after heating it up, rashalaga a mass of 2.8 grams. Before heating, so this is after heating. Then before heating, the mass was 5 grams. So that means before and after heating, when this learner heated the material, there was the aluminum trichloride and there was also the number of molecules of water. So when we heat the water, when we heat the substance up, the crystal up, and water gets evaporated from the crystal, the mass reduces from the aluminum trichloride, which has water, which has 5 grams, and the mass reduces to 2.8 grams. So after heating, the mass of the substance was smaller. So now we must find the number of moles of water molecules in the aluminum trichloride before heating. So in other words, H2O, how many moles of H2O were there? Before heating. So to solve this, we must first find the mass of the water that has evaporated. So mass of H2O that evaporated, that will be the mass before heating minus the mass after heating. Can I ask, do you understand why we have to take the mass before heating and the mass after heating? Eh?
I think so that you can know how much mass has been used up.
How much mass of which substance? The water or the aluminum trichloride?
What?
The water, ne? That's because that's the one we need to find the moles of. Remember the formula for number of moles, K n equals small m over big M. So at least if we find the mass of the water, we can find the molar mass of the water, then we can also find the number of moles. So you are correct, Musa, to say you feel okay, we will need to find the number of moles of the water that was evaporated. So we found the mass at least, and that's 2.2 grams. So with that mass, the next step we can do is find the mass ratio. So this mass ratio is going to be the mass ratio of aluminum trichloride to water. Ne? So we've got 2.8 grams is compared to 2.2 grams. So this ratio, think about it like when you're mixing Oros or Wild Island, right? There's always a ratio. So you'll have 1 part of the concentrate, and then you'll have 1, 2, 3. So in other words, for you to have 4 liters of dilute orange squash, you'll have to mix 1 liter to 3 liters of water. So in the same way, when we think about ratios here, in order for us to have 5 grams of our initial substance, we need to have 2.8 grams of aluminum trichloride and 2.2 grams of water. So when you add these two together, they offer that 5.0. So the ratio then of the aluminum to the water becomes 2.8 to 2.2. Now we can do the next thing, which is find the mole ratio. So we found the mass ratio. Now we can do the mole ratio. And the mole ratio is going to be mass over molar mass for the salt. AlCl3. And we do the same for the water, H2O, MH2O. So the mass of aluminum trichloride get 2.8 grams, and the molar mass of aluminum trichloride, which we can read from periodic table, the molar mass of aluminum and then the molar mass of chlorine, and then we will have to multiply that by 3. So let's quickly look for these two elements on the periodic table. So aluminium, the molar mass is 27 grams per mole, and chlorine it's 35,45 grams per mole. So times 3, that will be 35,45 multiplied by 3, it's 106,35, and then we add that to 27 for aluminium, and then the molar mass of aluminium trichloride is 133.35 grams per mole. So does everyone understand how we got the molar mass of aluminium trichloride? This one here. Mosan Magdalene? It's a loader. Oh, okay. Yeah, in a low basone, I'm sure it locomotes. It does that. Let's give it time. I can maybe refresh the page. Okay, it doesn't want to refresh that way. It's fine. So then we do the same for the number of moles. I guess we're doing the mole ratio. Moles is number of moles, N. So it's 2.2 grams over. For hydrogen, the molar mass of hydrogen, 1,01 grams per mole. And the molar mass for oxygen, 16,0 grams per mole. So that means the molar mass of H2O it will be 2.02 plus 16, and this gives us 18,02 grams per mole. And now we substitute that there, 18,02 grams per mole. So that means if we take 2.8 divided by 133,35, then we get 0.02099 is to 0,12 there. So we can convert this ratio to whole numbers by dividing by the smallest amount. So the smallest amount is 0,021. So if we do that, we will get 1 is to 6, roughly. So that means in that crystalline formula, so if we do this, let's say we divide here by 0,020. Then on this side, we'll get an answer 1. And on this side, this number divides into there 6 times. So our crystal, some water molecules that crystallize it. Right? For every one of these, we will have 6 of the water molecule. And that's what this calculation is has done for us over the last two steps. So what this tells us, Kyore, in order for this crystal to form, we will have one aluminium trichloride bonded with 6 moles of water. 1 mole of aluminium trichloride will bond with 6 moles of water for us to have the crystal. And we can do this to other types of salts or crystals, including copper sulfate. But yeah, that we can do at another time. So far, are we still together?
Yeah.
Okay. So just another thing, the last part area dirilenia waters of crystallization, but also combined with the other of quantitative aspects of chemical change, the other parts that we've done, they simply fit into the bigger picture, yeah, how we make sense of the numbers that go in our chemistry. So in other words, in the last example, something was heated up. So because it was heated up, it changed its composition. And because it changed its composition, we notice a change. Maybe the change in mass is a telltale sign, etc. Then we just use that information to discover what is at the end of that result. The next thing that we're going to look at, and I think this also goes into concentration, number of moles, and volume. So remember, so far we've been dealing with number of moles is mass of substance divided by molar mass. And Musa Karupola, in your grade 12, when we discuss chemical change, rates and exchange of reaction, Le Chatelier's principle, we always have this formula, C equals N over V, which also equals small m divided by big M times V, because when we substitute this there, let me just use a different color. So if this is that, then when we substitute this, we will have this in this formula there. Ne? So from grade 10 to grade 12, we use this formula quite a lot. It's just in grade 10, which is the grade before, like where Magdalene is, and I guess 2 grades before you are in matric, when I was what we learn from this theory, we build on the concept. So in the next grade, we apply it, but we don't apply it to a limited extent like in the grade before. And in matric, we go deeper and deeper because now it goes into finer aspects of the chemistry itself. So we're gonna do a little bit of this this formula here, because we've already looked at this one. And in this, we're going to talk about what's called amount of substance. So amount of substance, we'll start off with the molar volume of gases. Ne? So molar volume of a gas. So 1 mole of gas occupies 22,4 dm cubed, and this is at standard temperature and pressure. So when we're dealing with gases in physical chemistry, and I guess in inorganic chemistry, we often talk about standard temperature and pressure. Um, and this applies to any gas that is in standard temperature and pressure. This 22.4 dm cubed. And we'll learn, so when we do our grade 11 physics on this part, we'll talk about this and gas laws, ne? Gas laws. All right. So what this then means is that if we have hydrogen gas, 2 moles of hydrogen gas will occupy a volume of 44.8 dm cubed. So volume, remember, is a 3-dimensional measure, right, of the space inside. If we have just a dot, maybe we have 0 dimension. If we have a line from the dot and something as small as that dot or that line can move anywhere along that, then that becomes 1 dimension. If we take that 1 dimension and we project an area, or we square that length, then whatever it is that was small enough can now move in here. And if we take then the same 2D shape, that's 2 dimensions, so the units here would be meters, the units here would be meters squared. And if we take that area and we project it above the floor, then we get a volume. And that gives us a 3-dimensional object, so its units are cubed. So dm cubed, I believe the D stands for deci, but I just want to check dm. I just want to check. But I remember it's decimeter, I think. dm cube, yeah, decimeters. So dm cube stands for decimeter, and a cubic decimeter ilgana 1 liter. So in your house, the jug you measure milk in when you are baking, or the liter long life milk that's in the dispensary waiting to be opened, it's like a freezing, or the liter of concentrate, Wild Island or Halls or Oros, it doesn't matter. That same 1 liter, that volume is the same as a decimeter, a cubic decimeter, rather, not a decimeter, cubic decimeter. Yeah. So 1 dm cube equals 1 liter. So in other words, 1 liter can take up the space here, or rather can be filled up by 1 mole of gas. So 1 liter of space is filled up by 1 mole of gas. And this is the same for any gas. Any gas you can think of, whether it's carbon dioxide gas or oxygen, ammonia gas, someone passed gas, doesn't matter. But oxalayo, the amount of space that 1 mole of gas can occupy is 1 liter. It's 1 cubic decimeter, 1 dm cubed. So far, we're still together.
Yeah. Mm-hmm.
All right, cool. Then I also, okay, let's check out the concentration, right? So when we're talking about molar concentration, the concentration, again, it's known as the number of moles of the solute divided by the volume of the solution. So this is when we are looking at molar concentrations of liquids. And a typical solution, so solution is made by dissolving some substance in a liquid. So we take a solute and we mix it with a solvent. So if we take sodium chloride, that will be our solute, and H2O would be our solvent. So this would be an example. And in that example, we'll be able to see the difference between the solute and the solvent, and those two give us a solution. So the definition of a solution is dissolving some substance in a liquid. And the amount of substance that is dissolved in a given liquid is the concentration of the liquid. So concentration becomes the amount of substance dissolved. So amount of solute dissolved in solvent. So in other words, think about it this way. You have a cup, komiki, that you can think about anywhere in your house. And then you start pouring salt. Or sugar. Let's take sugar, since we probably would experiment with that. If we chela too much coffee in your hot water, what happens to the flavor of the coffee? On a look which means out to there. You put hot water in it. And then after you put hot water in it, you're gonna pour coffee. Now when you pour coffee, you pour half a teaspoon of coffee. Is the flavor or the concentration of the coffee for half a teaspoon of coffee gonna be the same as the concentration of coffee for a full teaspoon of coffee? Which one has more concentration?
A full teaspoon.
Okay, so the full teaspoon. All right.
Yeah.
Then let's say I add another teaspoon. So now I put 2 teaspoons of coffee. What happens to the concentration of my coffee?
Because even more,
Over-
increase.
Increase
compared to
again.
Yeah.
All right. So that same way of thinking, we can also think about it the molar concentration of liquids. So the more we increase the solute dissolved in the solvent, the higher the concentration. One. And the units for concentration are moles, number of moles per dm cubed. Ne? That's because this one is measured in moles and this one is measured in dm cubed. So the units then become mole per dm cubed. And we can do a quick calculation just to see if we grasp the concept. So, as an example, because we're doing molar concentrations of liquids, we're given 3.5 grams of sodium hydroxide, and it is dissolved in a volume of 2.5 dm cubed of water. And we must find the concentration of sodium hydroxide solution. In moles per dm cubed. So we must find the concentration, and then the first thing that we start with is the number of moles equals mass over molar mass, and this equals 3.5 grams divided by 40,01 grams per mole. So when we calculate that, that gives us 3.5 divided by 40,01. So 3.5 divided by 40.01. That gives us 0,0875 moles. And now the concentration, which is the next step, will equal number of moles divided by volume. And this would be 0,0875 divided by the volume, which is 2,5 dm cubed. And we can simply divide by that answer by 2,5. And then we get 0,035 mole per dm cubed. Hi, Nobutle.
Good afternoon. Good evening.
How's it going?
Good, thank you. How are you?
All right, it's going well, thanks. So I just want to recap. So, because in the last half hour, we did and we extended what we know from the last bits that we studied, ne? Nobutle, I think do you have access to the Jamboard? I just want to start from slide 1 and explain everything. Then we can get to where we are now.
Yes, I have access.
All right, cool. So we started off with, last week we were doing quantitative aspects of chemical change. And we were looking at the composition of chemical elements, chemical compounds rather. So in one case, the compounds would have the formula given, and we would have to find, like, if it's H2O, what's the percentage by mass that the hydrogen occupies, and what's the percentage by mass that the oxygen occupies. And then we had another type of problem where the opposite is true. We're given that a certain atom occupies this much percent by mass of a certain molecule, and then we must find the chemical formula. And then another third type of those types of problems is one where we have the product at the end of a reaction, and then we must find what the original reactants were. And this is based on the quantitative stuff that we know about the elements. Now we today started with the fourth type, which is crystallization, waters of crystallization. So you see crystals when they form in nature, And I'm not talking crystals limited only to things like salt. Crystals you can find in a lot of uh, like almost everywhere. So even dirt, when you look at it under a microscope, a specific type of soil, let's say it's a soil that you find at a geological formation that has mostly silica or iron or aluminum. So, like in this example, we have aluminum trichloride, which I'm not really sure where it comes from, but let's assume it's a crystalline substance. And now, for it to be crystalline, it normally has some amount of water in it so that it can exist in crystal form. So, that amount of water, we are then going to learn how to calculate it in the next steps. So, we start off in the example that we started off by having the mass of that substance that has water in it. And how we see that it has water in it, we see with the formula for H2O, and next to it, there's a number that shows that a certain number of moles multiplies that water that crystallizes that salt. So before heating this molecule, we had 5 grams. And when we heat it to evaporate the water, we have 2.8 grams of that remaining. So that means the water has a mass of 2.2 grams, which is the difference between the initial mass of the substance and the mass after heating. Now, once we have the mass of the water after of the water itself, we compare the ratio of the mass of the salt itself to the mass of water. So in other words, as this is 1 unit, how much in proportion of this do we have to the water? How much in proportion of the aluminum trichloride do we have relative to the water in the crystal? So, but we start off that calculation with the mass. And then we extend the same line of thinking with the molar mass, which we simply work out by looking at the periodic table so that we can find the molar mass of each of the compounds. So the molar mass for aluminium is 27 grams per mole, and the molar mass for chlorine is 35.45. But chlorine, there are 3 chlorine atoms in the substance. So we multiply that by 3 and get 106.35 grams per mole, which we add the 27 to, and then we get 133.35 grams per mole. Nobukla, I just want to check in with you. So far, are you able to follow this discussion?
Not entirely, but yeah, I
Not
am
entirely.
following. Yeah, I'm just going through the notes afterwards because the
Okay.
revision sessions are quite short. But understand because I joined an hour later.
Oh, okay. And then the second, okay, thanks for that update. Remember, you can also share those reactions here. These ones. Then the second thing we do is to find the molar mass of the water molecule. So we know that the water in the crystal is 2.2 grams, but its molar mass is simply the molar mass of hydrogen times 2 because there are 2 hydrogen atoms in one molecule. And then we take the molar mass of oxygen, we add the 2, then we do a bit of math. So the math that we do, we take the masses of the substances, so the aluminum trichloride alone and the water, and we compare them as as this equation, n equals small m divided by large M. So we take that ratio for the aluminum trichloride and we do the same for the water molecule. And what ends up happening is if we divide the mass by the molar mass, we get we get irrational numbers. So for aluminum trichloride, we get 0.021, and for the water, we get 0.12. So if we divide by the smallest number on both sides, then on the left-hand side of the ratio, we get 1. And if we do the same on the right-hand side, we get the number 6. Now, what does this tell us? This is a very important revelation because it tells us that for every 1 mole of aluminium trichloride, we need 6 moles of water to form a crystal. That is why these are called waters of crystallization, because you need a certain amount or number of moles to form a crystal with that salt. So that's how we solve the fourth type of problem. Then we moved to a different type of discussion, which speaks about the amount of substance, but primarily in a gas. And then later on, when you joined the discussion, Nobuhle, it was with molar concentrations of liquids. So we'll start off with molar volumes of gas. There's one thing that we always need to keep in mind when coming to the molar volumes of gas, and it's that 1 mole of any gas, 1 mole of any gas, be it H2 gas or ammonia gas, doesn't matter the gas, 1 mole occupies 22.4 cubic decimeters. And now, don't be startled by this unit. The cubic decimeters is simply equivalent to 1 liter. Any 1 liter unit you can think, a measuring unit you can think about, whether it's a kitchen jug or catering jug or whatever they call, that has a graduation to show 1 liter mark, a graduated cylinder in a chemical lab, I guess a 1 liter engine in a car. But that same 1 liter, that volume is the same as 22.4 cubic decimeters. And that's the volume that 1 mole of gas occupies. So when we know that information, in fact, that information is all that we need to know for the molar volume of gases. Now, the next thing about that has to do with moles is the molar concentration of liquids. So, again, the analogy with cordial, when you have is it holes? I think holes is 1:4, right? So when you have 1 of those, and so 1 of the concentrate and 1, 2, 3, 4 of the solvent, right? When we add 1 of these to 4 of these to get 5, this gives us 5. We find that we've reduced the concentration, so we've diluted it. So in other words, just as you can think of, earlier I made the example, the more you increase the number of spoons of coffee in your coffee, the more concentrated it becomes. That also works in reverse. If you don't put as many spoons of coffee in your coffee, then it doesn't get as concentrated. So concentration simply means the amount of solute, or that which you will dissolve, in a solvent, the solvent being that which dissolves your solute. So I think this is where we were carrying on our conversation. So we were gonna look at this kind of calculation for concentration. So in our example, we're given 3.5 grams of sodium hydroxide. And we're also told that it's dissolved in 2.5 liters of water. And now we must find the concentration of the solution. And our calculations like this, they become important because in some cases, I believe we have to work out a standard solution. And what a standard solution does is it's like you benchmark a solution relative to others. So, but we'll get into that when we do them. But it's just important for now to understand how we come about working out the concentration of a substance. So, in order for us to complete the objective, we have to first find the number of moles of our substance. So we've got, wait, before I carry on, our call's gonna end soon in about 5 minutes. Can I hang this one up, start a new one, and then invite you to that new one so that we are uninterrupted? At least before that happens. Yes, I'll do that. So let me quickly do that, and then you'll just get invites to the next class. Just give me 2 seconds, a few seconds. Turn home screen. New meeting. Oh man. Get that, do it for sure. Don't get that, do it for sure. Hey, you're back. We are back. We are back. We are back. We are back. Sure. All right. So where was I? I was saying yes. So we start off first by looking at the number of moles of sodium hydroxide. And we can start off first by working out the molar mass of sodium hydroxide. So for sodium, the molar mass is on the periodic table, it's number 11, row number 3, column 1, and the molar mass is 23.0 grams per mole. And for oxygen, the molar mass of oxygen on the periodic table, it's element number 8, and its molar mass is 16.0 grams per mole. And hydrogen, it's number 1, so its molar mass would be 1.01 grams per mole. Now we add these, it's 23 plus 16, that's 39, and this is 40.01 grams per mole, which is this number here. So we're told initially that the mass of sodium hydroxide given is 3.5 grams. So we simply divide the 3.5 by the 40.01, and then that gives us 0.0875 mole, which is the number of moles of sodium hydroxide in 3.5 grams of sodium hydroxide. Now, we're told that this number of moles are dissolved in 2.5 liters of water. So the concentration simply becomes the number of moles divided by the volume. So number of moles is the mass of the substance divided by the molar mass, and the concentration is the number of moles divided by the volume, or also the mass of the substance divided by the molar mass times the volume. So in other words, we would still get to this answer if we said the concentration is 3.5 grams divided by the molar mass of the substance is 40.01 grams per mole, and the volume is 2.5 dm cubed. So even if we had just gone with this substitution from the word go, we would still get the same answer, and our concentration would be 0.035 moles per dm cubed. Namusha, I don't think you got this part, but the units for mass are grams. The units for molar mass are grams per mole or grams per mole. What's on your mind?
I'm following.
You're following, okay. So I was just going over the analysis of the units, right? So in this, the N is measured in moles. The number of moles is just mole, like that. And here, when we have the mass divided by the molar mass, it's the same as having grams divided by grams per mole, and this is grams times mole per grams, and the answer there simply gives us mole, which is the unit for number of moles. And then for concentration, I'll just make a space there. So that means for concentration, we will have moles divided by volume, dm cubed. And this is why the units are mole per dm cubed. So I just wanted to clarify that concentration units are mole per dm cubed, and yeah, that's because we have this part here of a volume. So it's number of moles divided by the space that they occupy. It looks like there's more than one type of calculation for concentration. So we can do another one. So we've got a volume. It's 1 dm cubed. That's our volume given. And we need to prepare potassium permanganate, KMnO4. No, but isn't that what you work with at your plant?
Yes, yeah, we do work with potassium manganate.
Permanganate, yes. So we need to find the mass of potassium permanganate needed to make a solution with a concentration of 0.2 moles per dm cubed. So we need to find the mass. Okay. So again, concentration is mass divided by molar mass times volume. We don't have this mass, but we have the concentration. We can find the molar mass of our potassium permanganate, and we're also told the volume that the solution must occupy. So that means we can wait. Is everything all right? Did someone write on the... Is everyone...
Sorry.
Oh, okay. Everything is sharp.
Yeah.
Okay. Okay, great. All right. So we can do this in a number of ways, but since we don't know the mass, we can make the mass the subject of the formula. So then that mass that we're looking for is going to be the concentration times the molar mass times the volume. So we know the concentration, it's 0.2. The molar mass of potassium permanganate is gonna be the molar mass of potassium plus the molar mass of manganese plus 4 times the molar mass of oxygen. And on our periodic table, potassium is in group 1, row 4. It's element number 19, and its molar mass is 39.1 grams per mole. Manganese Mn is element number 25, row 4, group 7, 7b. Its molar mass is 54.9, and oxygen is going to be 4 times 16,0. So we simply add those to get the molar mass of potassium permanganate. So 4 times 16 plus 54.9 plus 39.1. So that gives us 158.0 grams per mole. And we know that the volume is 1 dm cubed. So that means we can substitute all of this here. So it's 1 times 158.0 times 0.2. And our answer is gonna be, I hope I got it right, 31.6 grams. So the mass of potassium permanganate that we need to make 1 liter of a concentration of 0.2 moles per dm cubed, we're going to need 31.6 grams of potassium permanganate. So I just did it directly. I worked it out directly. In our learning guide, how it's worked out, step 1, using the concentration equals number of moles divided by volume formula, then the number of moles is the concentration times volume, which is 0.2 times 1, which is 0.2 moles. So once you found the number of moles as 0.2, then the mass, which will equal number of moles times molar mass, and this would be number of moles is 0.2 and the molar mass is 158.0, and then the mass then becomes 31.6 grams. So there's 2 ways to do it. The first one is direct, just work with the concentration formula where you substitute N equals M over big M into that equation, and then you just substitute every bit of information that is given. So we're given the concentration, we found the molar mass, and we're also given the volume, and then that gives us the mass of substance that we must use. Another variation of this type of calculation, we need to find how much sodium chloride. So find M, mass of sodium chloride, table salt, that we need to prepare half a liter, 500 cubic centimeters. Oh yeah, it is half a liter. And half a liter of salt with a concentration of 0.01 moles per dm cubed. Okay, so first things first, unit conversions. Do any one of you ladies want to take a guess how we're going to convert from cubic centimeters to cubic decimeters? Who wants to guess? Any takers? None. All right, so when we have all right, let me put it like this, ne? The conversion factor for cubic decimeters to cubic centimeters. 1 cubic decimeter equals 1,000 cubic centimeters. So if we have 500 cubic centimeters, then we can work out how many decimeters that is. So if we have 500 cubic centimeters, we multiply that by 1 cubic decimeter, and that gives us 500 cubic centimeters times 1 decimeter divided by 1,000 cubic centimeters. So we will have 5 divided by 10 dm cubed, and this is half a liter. So that's how we convert So we start off first by converting the volume that we're given, which is not in the unit of volume that we need to work in, which is cubic decimeters. And the conversion factor for decimeter and cubic centimeters is that 1 liter equals 1,000 cubic centimeters. No, which I don't know if you've seen, but like some car engines are specified in cc.
Yeah.
Yeah, so
Even breast implants.
I mean, okay, you can take it that far, I guess, but yeah, you seen mus like a okay, what's a cc engine you can think of? Because I want to make I want to draw the association to DMQ. Yeah. Let's say, yeah, like an engine with 1,000 cubic centimeters would literally be a 1 liter engine. Yeah, a vehicle with an engine of size 1,000 cubic centimeters or 1,000 cc literally has 1 liter engine. So then we can then find the number of moles. So we are given the volume and we also have the concentration. So we have a volume of 0.5 dm cubed and a concentration of 0.01 mole per dm cubed. So if we know that the number of moles equals, or rather, the concentration of a substance equals the number of moles divided by the volume. This is a formula we're given. So then that means 0.01 mole per dm cubed equals number of moles we don't really know, but we know the volume, it's 0.5 dm cubed. So this and that are multiplicative inverses, they'll result in 1. And we take 0.5 and multiply it by 0.01. Then the number of moles becomes 0.005 moles of sodium chloride. And then if we want to find the number of moles equals the mass divided by the molar mass. That means the mass will be 0.005 mole equals m divided by. Now the molar mass of sodium chloride would be, sodium is 23.0 and chlorine is 35.45 grams per mole. 23 plus 35.45 will be 23 plus 35.45 is 58.45, and we multiply that by 0.005, and this gives us the mass of salt required to give us a concentration of 0.01 mole per dm cubed. Would be 0.29, did I get the math right? Grams. Which is mass of sodium chloride needed. So in other words, think about 1 gram, how much a gram weighs. Now we need to take 30% of a gram, mix it in half a liter of water so that we have a concentration of 0.01 moles of sodium chloride per liter, per dm cubed, per cubic decimeter. So this is what this tells us. In order for us to have a concentration of 0.01 moles per cubic decimeter, we need 0.29 grams of salt. So far, are we still together?
Yeah.
All right. So the next type of calculation that's done is called a stoichiometric calculation. Stoichiometric calculation. I'm going to look up what that means. Calculation. I have no idea what that means. So stoichiometric. Let's look at the meaning first. Right. Okay. So stoichiometry means the relationship between the weights of reactants and products before, during, and I guess after chemical reactions. So we basically measure the relationship of weights before so reactants and products. So before, during, and after a reaction. So in other words, let's say we've got, it doesn't matter what's reacting. So this one has a weight or mass before the reaction, or rather we have a mass before the reaction, and we also have a mass after the reaction. And we look at the relationship between the two. So that's the long and short of stoichiometry. That's the long and short of stoichiometry. So we will be using that to know how much product will be formed in a chemical reaction, or how much reactant is needed to make a specific reaction. And again, these kinds of calculations become important for our grade 11 and 12 work, but we're just starting it here because this is where the basis of how we add and think about how we add and calculate these things comes from. So once we do these, so we'll do these for physical chemistry, which is where you play around with volume and pressure for gases to work out the same types of calculations. And then for grade 12, we'll do that for rate and exchange and extent of reaction, as well as for what's this? Chemical change. Yeah. So, but the same calculations that we're gonna do here for stoichiometry apply in both cases, because we look at what reacts, we look at the balanced equation, and then we look at the products, and we assess the mass of reactant needed to make that which is a product. And the long and short of it is we'll have reactants, a balanced equation, and products. And in either case, we look at mass, molar mass. So we look at mass, molar mass, volume, and concentration. And I guess on this side, we also look at the same. Mass, molar mass, volume, and concentration. And then we also need to balance out the number of moles in either case. Okay, so we'll jump into an example quick. So we're looking at oxygen, and it's at standard temperature, standard temperature and pressure. So now just another quick one. Whenever we see the abbreviation STP, we are assuming that whatever it is that we're looking at, if it's a gas, especially if it's a gas, then it's assumed to be at standard pressure, or rather standard temperature and pressure. So standard temperature and pressure, STP in SI units. I just want to quote that so that I don't mislead you. Right, so standard temperature and pressure are a temperature of 0 degrees Celsius or 273.15 Kelvin. Now the Kelvin scale is the one that gives us absolute zero. That's where we can't go beyond temperatures that are below 0 Kelvin. Like it's beyond what we know as freezing and cold. Excuse me. And then for pressure, pressure at STP, it's 1 bar or 100 kilopascals. 100 kilopascals. Pascals is a unit of pressure. It's force applied over a unit area. So it's effectively Newton per square meter. So if you think about force being applied on an area, if you want to think about this by looking at it from the side, then you'll have a force acting on a surface like that. So this here would be the area. So then, yeah, that's another way of looking at pressure. Yeah, so at standard temperature and pressure, we are looking at these assumptions, that the temperature is 0 degrees Celsius or 273.15 Kelvin, and that the pressure is 1 bar or 100 kPa. It's actually 101.325. But we'll just work with 100 kPa for now. So what volume of oxygen at standard temperature and pressure is needed to complete a combustion of 2 dm cubed of propane? So C3H8. The hint that we're given is that carbon dioxide and H2O are products. That means if we have C3H8, which is a gas, and we heat it up in oxygen, which is also a gas, we should get carbon dioxide, a gas, plus water, also as a gas, which is water vapor. But now we must balance out our equation. On the left-hand side of the equation, we've got carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. We've got 3 carbons and we've got 1 carbon on the right-hand side. So that means we must multiply the right-hand side where there's carbon by 3. So we've got 3 here, 3 here. That checks out. Over here, we've got 8 hydrogens on the left-hand side, and we've only got 2 hydrogens on the right-hand side, so we must multiply that by 4, so that we have 8 on either side. And in terms of oxygen, we've got 2 on the left-hand side. We've got 6 plus 4, which is 10. So that means we must multiply these ones here by 5 so that we have 10. So when we add these, it's 3 carbons, 8 hydrogens, 10 oxygen atoms, 3 carbons, 8 hydrogens, 10, so 6 plus 4 oxygens. So our equation checks out like this. So now when it checks out like this, that's step 1. We look at step 2. So all the reactants are gases, and we can use the mole ratios to do a comparison. So the ratio of oxygen to propane in the reactants is 5:1. So we've got 5 oxygen reacting with 1 propane. So we need quite a bit of oxygen to burn up the propane gas. 1 volume of propane needs 5 volumes of oxygen. That means Um, the original question was we only have 2 liters of propane gas, right? So if we have 2 dm cubed, we might need 10 dm cubed of oxygen for us to get burn effectively 2 liters of propane gas. We will need 10 liters of oxygen. Kind of makes you think how much oxygen that's needed for breathing is needed to burn anything. But yeah, we can end our class here for the night. Before we end class, are there any questions, suggestions, or additions?
I look right.
You are right. All right. Nobute, you are sharp. All right. Let me see y'all again to continue this discussion on Thursday. I can't believe it's Tuesday. I'm thinking it's Wednesday. So I'll see you ladies Thursday.
Okay, sharp. Bye.
Sharp.